Good morning to all. I am Dr. L. Sivaramakrishna, the coordinator of this Atal AACT program on 3D printing and design, 1 week Atal online FDP program on 3D printing and design. On behalf of the organizing committee, this program is organized by Department of Mechanical Engineering, University College of Usmania City, and Center for Product Design Development and Additive Manufacturing. It's a part of Center of Excellence in Usmania City. And this is an online FDP program. It is going to start now from November 2nd to November 6th. We are going to have altogether 15 sessions. And in these 15 sessions, you are going to in these 15 sessions, you are going to have different speakers coming from different parts of the country. So out of 15 sessions, one session is a mandatory stress management program. And the 14 sessions are, I hope the schedule is shared with you. So today, the first session, it is going to start with Dr. Padmanabhan Garu, who is the director of ARCA. He is going to talk about the recent the trends in additive manufacturing, global trends. So, sir is a very senior scientist working in ARCA, especially on powder bed technologies. He is going to share all his experience today in today's first session. And then followed by my session, where I will be speaking about the fundamentals of 3D printing and as well as some innovative applications which are unimaginable to think earlier when we use conventional process of manufacturing. Then we are going to have in the evening from 4 to 5:30 a stress management session today, right? So this is what you are going to have today in our speakers, the topics of that, and I'll be sharing to you all those topics to you. We will have a session 1, session 2, session 3. Session 1 is on emerging trends in 3D printing technologies, a global perspective, by Dr. G. Padmanabhan, Director ARCA Hyderabad. And session 2 was an introduction to 3D printing and its innovative application by myself. And session 3, stress management through mindfulness and wellness by Mr. Manas Ram, Art of Living Facilitator, Hyderabad. So we are going to have these 3 sessions today. Our first session starts at 11:40 and at 1:10 p.m. So at the end of general instructions to all of you is please mute yourself when the session is going on. When you have questions, you please post your questions in the question answer box and also in the chat box. At the end, you will be given chance. If please raise your hands, I'll make you panelists. You can I'll unmute you. You can even ask questions to the speaker. And you can post your question in the chat box also, question and answer in the chat box. Then we'll be sharing at the end of the session, we'll be sharing the link for your feedback and also as well as your feedback and your attendance link will be sharing in the chat box. Please post your attendance. For each session, we are going to put the feedback and the attendance link. So please, it is the same link, only in one link is enough. We are going to post it for each session. And then at the end of each speaker, we'll be asking anyone to give feedback. So please raise your hand. I'll make you to give to talk about little bit on this session. So that is also part of mandatory of AACT, or record the feedback of each session. And then at the end, you are going to have after all the sessions before validatory function, you are going to have a multiple choice question, 20 questions, which you have to pass. I hope all of you know. We should have 80% of attendance in this entire sessions. That is, you should attend at least 13 out of 15, and then you should also have 60% marks scored in the end exam. And you can then only, and after you submit the feedback, then only you will get the certificate. Then only you will get the certificate from the Atal AACT. So I requested all of you, please join the Cisco WebEx by entering first name as your unique ID, which I already given to you. And also your last name is your name. Once you enter this, then you can start the registration process. Everything is shown to you through video. Yesterday also I conducted demo how to join this one. And then we are going to have a demo session. Last day we are going to have a demo session of our technology, CPDM technology, with what you call SLM technology. We are going to demo. We are going to give demo on SLM, SLS, and PolyJet. Then we are going to give demo on FDP, that is fused deposition modeling. Then on the SLA DLP and the 3D scanner. So all these we are going to have in the last day. So very interested speaker are coming to you. Please don't miss any of the sessions. So you will be also have a hands-on experience, one session on the software like Ultimaker and Ultimaker Cura and as well as 3D Slicer. You are going to have on that day. I request all of you please switch on your laptops so that you will be able to do that work. We will be sharing all the details to you. I already put in the WhatsApp group how to download the softwares. We'll be sharing it to you again today. And then you can download it and keep ready when the session starts. And also before that, we'll give the steps how you can do biomedical modeling. We'll be sharing the DICOM file to your, I think in your email, we'll send to the DICOM file. If it is possible, you put in the WhatsApp, but the DICOM file size is very big. I don't know how far it is possible, but we'll share in the your email. Then you can download that DICOM file, and also we'll give the step-by-step procedure on how to convert the 3D that your DICOM file into your final BioCAD modeling. So each step by step will be explained. Parallelly, the speaker will explain. At the same time, you will have that handout with you. You can see it and do these things. So. Am I audible? Yeah, Mr. Mohammed Afzal, any issue? Hello? Hello, Mr. Mohammed Afzal. Sir, good morning, sir. Sir, good morning, sir. Good morning, sir. Sir, your voice is not audible, sir.
Yeah. Is it okay now?
Now it is audible, sir. Now it is audible, sir.
Okay.
Now it is audible, sir.
So, are we ready or?
Sir, we'll wait some more parts. We are set at 11:40, sir. Just 1 minute.
Sure. 11:40, huh?
Yeah, I'll just give.
So I'll just keep it on and then please let me know. Just one small clarification. What is the background of the participants? Your voice is not coming.
Sir, most
You
of
have to
them
unmute.
are, yeah, most of them are from engineering or faculty members, sir. Apart from that, we have people from industry also, like defense organization, other people also coming, and startup company people also there, sir. The 3D printing startup company. So, and we have some doctors also in this program, some participants from dental doctors, etc. So altogether, it's a mix of mostly faculty members, sir. Then you have other people.
Okay, faculty members from different colleges. Huh?
Different college across India, sir. Around 200 participants are there across complete pan-India program, sir. It is total from Uttar Pradesh, from far of the country also they are there, sir. From Cochin, from different places. Just now the inaugural program has finished, sir. Just now Atal AAC inaugural common program they conducted. Today 39 FDPs are starting. So they completed, sir. So our participants are again joining. So we will start within another 1 minute. 1 minute.
No problem.
Just we'll have introductions. I request my participant introduce you to the audience, sir. Then we'll start your presentation.
Okay. So I'll just keep it on. Let me know.
Please keep it on. చెప్పండి ఇప్పుడే కాదు నేను చెప్తాను వినండి Sir, we'll start.
Okay.
Sir, please switch on your videos.
Yeah, I have done that.
Good morning to all of you. I, Dr. L. Sivaramakrishna, coordinator of this Atal AACT sponsored 1 week online FD from 3D printing and design. And another coordinator, Professor Sira Venkatesh, on behalf of us and the Department of Mechanical Engineering, Center for Product Design Development and IT Manufacturing. I welcome today's honorable speaker, Dr. G. Padmanabhan Garu, who is the director of ARC, who has given us consent to give his valuable address on the first day on emerging trends in 3D printing technologies, a global perspective. Before we start the session, I would like to invite my research scholar, Ms. Shweta, to please introduce the speaker to the audience. Ms. Shweta, please introduce the speaker to the audience.
Good morning, everyone. Am I
Your
audible,
voice,
sir? Hello.
No, it is audible, please.
I, Shweta, research scholar at University College of Engineering, University, welcome you all to the 1 week online.
Please keep the mic nearer, Amma. Please keep mic.
Department of Mechanical Engineering, University College of Engineering, Osmania University, in association with Center for Product Design, Development and Additive Manufacturing, Osmania University. I feel privileged to introduce the speaker of first.
Hello, your voice is not clear.
PhD. Sir.
Your voice is not clear. Please.
Sir, is it clear now, sir? Hello?
No, it's clear. Please be loud. It is lagging somewhat. Hello.
PhD, IIT Delhi, for his work on welding of aluminum alloys. Sir contributed internationally in the fields of materials joining and application of lasers. Sir worked as a design and development engineer in Scientific Department of Science and Technology, New Delhi. Later, He joined ARCI Hyderabad to head the Center for Laser Processing of Materials. Sir developed industrial laser-based materials processing technologies such as hybrid welding, weld brazing, micro-machining, and additive manufacturing, biomedical, defense, and nuclear sectors. He is author of more than 100 publications, patents, and 4 book chapters. He also supervised 6 PhD theses in the fields of materials and manufacturing. Apart from his research and technological contributions, he developed innovative models for R&D transfer leading to successful transfer of more than 20 technologies and innovations of ARCI to industry. Sir has many awards to his credit. To name a few, Abdul Kalam Technology Innovation National Fellowship awarded by Indian National Academy of Engineering, Materials Research Society of India Medal, Distinguished Alumni Award of NIT Award of Science.
Hello? Hello? Over? Hello? Hello? Some lagging is there, internet problem.
Over to you,
Hello?
sir.
Hello? Sweta, please switch off your video and then speak. Switch off your video. I think it's taking some internet.
Okay, sir.
Now you can speak. Now you can speak. Hello? Yeah. You're done? Okay.
Presentation.
Okay. Sir, we invite you for the presentation, sir. Now I'm making you as a speaker, sir. So,
To give the option to share.
yeah, I am giving, sir. I'm giving. Sir. Now you can speak. Yeah, it is there, sir. It is given. Sir. It is given. Sir.
Yeah.
You can proceed. Thanks.
So, a very good morning to all of you.
Good morning, sir.
Participants from academic institutions, industries, and other sectors. Thanks to the organizers for inviting me to deliver this lecture. What I plan to do during this today's lecture is cover a little bit of what the AM landscape is today and what kind of growth trends we are seeing. Being a metallurgist, I am more familiar with metal additive manufacturing process, so I will cover that part of it in more detail in terms of what are the process issues, what are the metallurgical issues, and what kind of applications we at ARCI have developed, and finally the trends in metal AM. And depending on the time that is available, I will cover some part of ceramic 3D printing and then followed by functional materials using 3D printing. So, I'm not sure how many of the participants here are familiar with the so-called additive manufacturing technology. It is one of the youngest of manufacturing technologies in the world today, but at the same time, very hot topic in terms of the speed at which it is growing and the speed at which number of applications are getting added for this technology. But still, several challenges are there. I will try to cover them during my talk. So it's the process of joining materials to make objects from 3D model data, usually layer upon layer, unlike subtractive manufacturing. This is the basic definition of what is additive manufacturing. Any component, you develop a 3D model, and that geometry you slice it into layers and build each layer by running a feed source or a binder to form that particular geometry of that particular layer. And each layer you build over the other and try to get the part. This is simple principle. This is better appreciated when I show you a video. Additive manufacturing, why is it so attractive? It generates the product with less waste, less weight, automatically minimum environmental impact. It is also known as 3D printing. Throughout the talk, I kind of interchangeably will use the word additive manufacturing and 3D printing. And it's also called as solid free form fabrication, layered manufacturing, also called as digital manufacturing. And it provides a link, immediate link between what we have created on a computer virtually to a physical object that we built using this technology. So here is one small video of a very important component that we have developed at ERCI. It's called a wall block, and it has got multiple inlets, multiple outlets. It has gone through the whole process of design for additive manufacturing, topology optimization, then process the support structure design, the actual building of the component, removal of. So all these steps that are involved in this technique to get an actual usable component, we tried to cover. So instead of me giving you an oral explanation, please have a look at this video. So the conventional design is the block on the left, and then the new one is. You can see this, the red ones are the support structures. And that model is sliced into various cross sections. And each of these slice is selective laser melted. And after the build is over, this is using the powder bed technique. So the part is being taken out from the powder bed. And then after it is taken out, all the support structures have to be removed. And what we are trying to show here is how you have to design your support structures so that they are easily removable. And so that's the finished part. You can imagine the kind of complex geometry this particular component has got, and how easily we could design as well as do a weight reduction and develop a component in probably in 1 or 2 iterations itself. So a little historical background, starting from the first plastic-based rapid prototyping machine in '88, and then first metal AM machine in 1993. For several reasons, for example, aerospace industry is considered as incubator for additive manufacturing technology due to the ability of direct metal fabrication of titanium components. Titanium is an expensive material. Subtractively, you will lose a lot of material. So it became a good candidate sector for AM. Similarly, in biomedical industry, also we need patient to patient, the sizes, geometries of implants and devices are changing, and so customization is possible using additive manufacturing. And even for tissue growth and biocompatibility, the porosity that is required in the part can be tailored. The surface behavior also can be tailored so that there is better osseointegration. And that's the reason biomedical industry is one major gainer in for using the additive manufacturing. The total landscape, if you consider for additive manufacturing, today the plastics also can be, plastics are the first ones with which 3D printing happened. Then the metal parts, the smart structures, the electronic components. But each of these materials, depending on the size of the production, like whether you are using it for production or prototyping or home use, the choice of the technique varies. For example, the variation in terms of, let us say, when we are doing plastic 3D printing, we have methods like fuse deposition modeling. The same thing we may not be able to do or popularly use in the case of metal. Metal, we use selective laser melting or electron beam melting or direct energy deposition. Similarly, when you come to the electronic components of functional materials, the 3D printing methods like screen printing, aerosol jetting, ink jetting, lithography, such techniques are used. So today we have, the landscape is quite wide in terms of the materials that can be handled, the size of the production that can be handled, and a large number of processes that are available to cover these both verticals and horizontals, as I've shown in this chart. For example, here what you see is a 3D printed car based on a combination of ABS plastic with carbon fiber. You can see that it has been printed using the plastic 3D printing methods like binder jetting. This is in the case of this one, it should be the extrusion method. And then on the base structure, several other components have been built and a component made. So the kind of the design flexibility that it gives helps in conceptualizing different types of applications. And as small as a pin, what I have shown here using metal powders, you can create such very intricate geometries. You can call them mesoporous structures. That is the range that is possible. So all that today, where does it stand in terms of the numbers? What you see here is the projections are from a $6 billion industry to a $36 billion industry, 6 times growth in 5 years is what is predicted. Wohlers is one of the very famous market survey company in the world. And on the right side graph, what you're seeing is the number of publications that are coming out in the field of additive manufacturing and 3D printing. And it is exponentially growing. So what I would like to tell here is the speed at which the research is happening, as well as the absorption of the technology in actual application is almost happening exponentially, the growth. And in terms of the market distribution also, the pie diagram I have shown here is 40% is metal additive manufacturing, and then black 26% is polymer machines. And you can see, surprisingly, 7.7% is in composites additive manufacturing. And we are seeing the rise of electronic machines about 3.8%, and even ceramics 6.9%. So from plastic to metal to today, the kind of distribution that we are seeing in terms of where the AM activity is going is widening very fast. Again, within the metal, now I will concentrate more on the metal, then we'll go on to the other materials as we go along the talk. In the case of aluminum, let us say I'm just taking the example of aluminum alloys. This comes to show that it started off as the workhorse in metal AM, 55%. And as you see, its percentage in overall metal usage from about 775 tons of AM powders to about almost 15 times more powders that are projected for 2025. Even though the overall metal powder consumption for additive manufacturing is increasing, the aluminum usage level is coming down from a 55% to 21%. It means the trend is towards developing process friendliness with other metals also, like the ferrous, the other magnetic materials, the copper, tantalum, titanium. There is continuous increase in the portfolio of metals and alloys that are getting 3D printed. Just looking at the aluminum consumption itself, here I wanted to show this because what started off predominantly in the aerospace sector, slowly you can see that automotive sector is picking up and other service sectors are also picking up from a kind of a 6 million industry in 17 to about 300 millions is what is predicted. So AM is here as a very hot additive manufacturing technology, advanced manufacturing technology. And the whole community of additive manufacturing or advanced manufacturing has a very fertile field for research as well as technology development. Now, little bit do dissection in terms of where all this potential is coming from. What are the fundamental reasons why this kind of trend we are seeing in the growth of additive manufacturing? So I'll start from the top, direct translation of design to component. Then customization with no additional tooling. What we cannot subtractively manufacture, some of the complex internal features, we can do it with additive manufacturing. I'll give a simple example. When we want to make a hole in a component, drill a hole in a component, it is always a vertical, a straight line hole that we can drill. Why is it so? Because we can only drill vertically in a straight line only, so we cannot make holes which are not non-linear or in a curved fashion. Okay. Of course, you can do it in casting process, but there also it's not a very easy thing to make holes of complex geometries. But additive manufacturing gives you a great freedom in terms of, because you're building the material or the component layer by layer, you can build complex internal structures. I have shown a couple of them in the mesoporous structures and all. And then because the flexibility that it offers, and sometimes because you can't create hollow structures, you have to only create solid structures, or you go in for solid with a lot of weight in it. Since you now have the possibility of making lattice kind of structures, you can make you can target lightweight structuring. Then near net shaping, the next advantage. Then once you are not subtracting material, you are reducing the waste. Then lead time for development is very short, because you have an idea in the mind, you make a design, a CAD design, convert it into a sliced model, and then transfer it into your AM machine and then start building it. You will face a lot of building issues, but then they can be solved. And what takes 6 months in a usual development cycle can be brought to weeks in the case of additive manufacturing. And then one AM machine can build all kinds of parts. So the footprint is very small. What you have a big factory, you can do it in maybe one machine in a room of something like a 20 feet by 20 feet. So the space requirement also may be less. And then on-demand manufacturing, you think about something and only want to try it out, like prototyping, you can do it. And then today we are seeing excellent scalability is the latest attribute that is coming up. So people are making big lasers, big laser assisted additive manufacturing systems, like one machine incorporating multiple lasers and building them very fast, or combining the laser based deposition with other hybrid methods like very high deposition methods combined with features being deposited by laser. So there are several variants coming up. So even the scalability issues are being addressed now. Now, having talked in general the advantages of additive manufacturing as a advanced manufacturing tool, why aerospace sector has imbibed it or implemented it in a big way. What are those advantages? Like we all know in aerospace, lightweighting is important. So it is possible with AM. And we also have to incorporate several components and subsystems in limited space. So since it gives us geometrical freedom, so that's where we can draw the advantage from AM. And similarly, you can avoid welded joints and such things and consolidate number of components into one single assembly. For example, that video that I have shown you, it is actually a combination of 6 inlet outlet valves. All that, instead of assembling into one block, has been now built as single block. The moment you have no assembly requirements, weld joint requirements, the confidence of designers is higher to take that part. And then next part is reduced development time. So, and then this is the market size now. So I've just given specific examples of what are already in flying. The first example is the drag reduction vanes around cargo flight door in an aircraft, that cargo flight. So each vane has a different geometry. And then the numbers that you require is not very high. So you can't establish a full-fledged manufacturing facility for that. So you have one AM machine in which design after design you keep feeding and get the geometries that you're looking for. Then satellite antenna bracket, we talked about the design, geometrical design freedom that we get. What could have been a very, very straight lines and angles kind of a bracket has become simple like a web. And here in a rocket accumulator assembly also, 78% reduction in welding by 78% is what they have achieved. And in the latest GE engine, it's a demonstrator at this stage, 855 subtractive manufactured process reduced to 12 additive parts and reducing the part count. It helps a lot in productivity, and it's not only productivity, but it showed that 5% weight reduction is possible, and that leads to about fuel consumption reduction. Again, another example of weight reduction, what you make conventionally and what you can make using additive manufacturing. Another structural component, it is a plasma deposition technology. Even though it is a coarse deposition technology using wire as the feedstock and plasma torch as a heat source, and productivity has also been improved substantially. You almost build a near net shape component 50 to 100 times faster than the powder bed techniques, but 25% lighter than a forged part. And then they were able to do it very, very fast, the development of this component, and a saving of about $3 million an aircraft. And we talked about the very fine channels that we can create inside the components. So effective thermal management systems through like a heat exchanger with a very odd shape. What you are seeing here is not a typical cuboid or something like that, which we usually see in our engineering components. You can see a kind of a small segment with different features in it, curved features in it, non-linear, with conformal cooling channels in it, built by additive manufacturing. So this gives you an idea of the flexibility. Why is it attractive in biomedical industry? I'm giving you advantages from I mentioned a couple of them from the geometry point of view and the osteo integration point of view and the customization point of view. From the material point of view, some of the popular materials used in biomedical industry, the cobalt, chrome, moly alloys. With additive manufacturing, it was found that you can achieve 99.9% density and low metal elution compared to the as-cast alloys and cheaper also. And low metal elution means less toxicity in the body also. Similarly, stainless steel 316L is a very popular material. High solidification rates results in avoiding the manganese sulfide formation, which results in chromium depletion and results in pitting corrosion in these parts is avoided when you do additive manufacturing using laser-based powder bed technique. Similarly, SLM produced nitinol was suitable for human mesenchymal stem cells. I don't know this word too much. I'm not a medical person. And that's the advantage they have found. And niobium alloys, which are also used, very high temperature of processing is required, which is achievable by additive manufacturing. So these are some of the very popular additively manufactured components, applications in biomedical industries. The lower jaw, the lumbar vertebrae, tubular femoral bone, then frontoparietal temporal bone. Like this, there are several components which are already being used in a very customized manner for different patients. Now, the next sector is the automotive sector. Automotive sector, as we know, is a very conservative sector when it comes to incorporating any new manufacturing technology, because the industry is very competitive. The profit margins are very low. So unless it is all very much totally proven in terms of techno-economics, they will not take up any new innovation easily. So today we can't boast of a big penetration of additive manufacturing into automotive industry, but it is happening. For example, the way the developments are happening in the industry, like autonomous vehicles, electric vehicles, we are all talking of digitally connected transportation. So these are all leading to need for advanced technologies, and they want to reduce the number of steps and components of manufacture. Thermal balance, which I mentioned earlier also in production techniques like pressure die casting. Then reduction in weight, like in aerospace, here also they need light weighting. And quick turnaround of parts, of part development, and then customization and personalization. So these are all the new needs that are coming up in the automotive sector also, which are leading to this industry guys looking at AM as a possible good technique for them. But I mentioned that the absorption is not that fast. There are technical reasons as well as business reasons why this is not happening. For example, the size of the parts that you are able to build as of now is not very big in the case of additive manufacturing. Combination of materials building is a still research stage area. And major problem is the qualification and certification. Don't have established standards that AM built part of X material. These are the properties that are achievable or to be achieved, then only we can accept it and incorporate into our design. This kind of standards are still evolving because automotive industry produces things in large numbers with Six Sigma kind of quality requirements. Unless the process and technology is robust, they cannot incorporate it. Similarly, on the business side, you don't have many people with the skills to operate the AM technology. Then there are issues of IP protection. Even today, it is highly capital intensive today. Maybe in future, they become cheaper. I'll tell you, I'll come to that data also. And then today, the return of investment doesn't seem to be very attractive. And the technology is evolving so fast that what machine you think is the best today, probably in 6 months to 1 year itself, it may become obsolete. And the industry cannot again revamp their whole production line. But nevertheless, there is a very encouraging sign in terms of more and more automotive industries picking up this technology. For example, in the tooling, I'll show you an example also. General Motors has developed AM-based tooling and other accessories that are required. And they saved about $300,000 by AM tooling in 2 years' time. And they are planning to roll out about 20 different models of new models in 5 years, which is only possible when you have short development lead times, like in the case of additive manufacturing. And Mercedes-Benz looked at another domain where AM can be effectively used. That is some of their older truck models, which are still running, and the spares, the legacy parts, have to be made in very small numbers. In such case, they cannot have very high expensive lines set up for making few numbers of these spare parts or replacement parts. And they found AM as a good solution for meeting that kind of requirement. So each industry like this, I came across the Ford doing big investments, Volkswagen doing big investments, and several other companies, BMW, Audi. All these companies are in fact creating joint centers along with AM companies to realize the full potential of additive manufacturing in the automotive sector. For example, I told about tooling. A stator boring tool for aluminum motor body. So this is a Kennametal developed tool. Used in e-mobility components are typically machined on smaller HP CNC centers. And then by additive manufacturing, this boring tool could be made very, very lightweighted, because of which very quick adoption of simple machining CNC systems could be done. And meeting the accuracy, roundness, all those things could be managed because the tool is good, all those things will come. And very simple machines were able to manufacture the components. Now, having talked about the various sectors, the various advantages, the potential, the trends of additive manufacturing, let us get a little technical now in metal additive manufacturing today. What are the different technologies that are available in the market? What you see here is blue boxes and a little bit gray boxes in the bottom. The blue boxes are the actual techniques, and the gray boxes are the companies which produce these machines globally. This is not comprehensive. Every day, new companies are getting added to this list, actually, almost on a daily basis. So we have the major categorization in terms of the powder bed fusion or sintering or binding method is the first vertical, and direct metal deposition is the second vertical. Then the solid state method of ultrasonic additive manufacturing, liquid metal printing, cold spray deposition. These are the other three verticals. It is difficult to get into all these methodologies and explain in one hour talk. Possibly during 1 week of FDP program, you'll be hearing talks on each of these techniques from different expert speakers. in the next 1 week. What I will cover today is some popular techniques, which we also at ERCI have a hands-on feel for it. What you can see in the first vertical, the second horizontal is the heat source, whether it is a laser beam, which is being used to melt or sinter the material, or an electron beam, or the shaping methodology is using a binder. And then within laser method, whether it is a melting method, or it is a sintering method, or it is a lithography method through binder, like photopolymerization method, like that, depending on the heat source, the shaping methodology, the technologies are categorized here. So I will talk of the powder bed AM system. You have a bed of powder on which a laser beam or an electron beam as heat source is scanned in the pattern that you program it. And wherever laser beam scans the bed, that portion gets melted and solidified. Then after that layer, you lower the platform or the bed by about 50 microns or 60 microns, spread another layer of powder, again scan the laser beam, melt and solidify. Like this, the process continues layer after layer, and at the end you have a part that you are looking for. So this is called the powder bed additive manufacturing technique. The other technique is the direct energy deposition technique. In this one, what you do is you have a heat source, you have a substrate on which you are building the component. Into the heat source, you feed the feedstock material either in the form of a wire or powder, and the heat source will melt it, and the droplets formed will get deposited on the substrate. And by moving your platform or the whole processing head itself in the way your component geometry is there, you can, in the XY plane, you can build that layer and lower the plane by that much distance, the Z plane, and then build the next layer like that. So here it is the deposition method, there it is direct deposition method, there it is fusion method. You have the material already in the bed where you are fusing it. Here you are depositing layer by layer. That's why it's called direct energy deposition. Each of them have their own merits and demerits. We'll just briefly look at that also. For example, if we compare these two processes, like the selective laser melting method or the direct metal deposition method, the second and the third column. The first difference is the thickness of the layer that you can build is about 20 to 100 microns in this case, and 254 microns in the case of direct energy deposition. This comes from the particle size that you use. If you use very fine particles in direct energy deposition, there's a problem of choking of the nozzles. That's the reason we can't use very fine powders. Because of the layer thickness, automatically your deposition rates will be different. Your dimensional accuracy will be different, and the surface roughness that you can achieve also will be different. To just give you an idea why the change in technique can cause what kind of changes in the part that you end up with. Then you have electron beam as a heat source. How is it different from laser beam as a heat source? Today we have machines which can give up to 6 kilowatts of energy. So, and then the beam scanning is not with the optical scanners that we use in the case of laser, but with magnetic systems, extremely fast beam translation without any moving parts. So you can imagine the robustness of the machine and the zero maintenance requirements of your scanning systems. Then the processing is done in vacuum, because unless it is vacuum, then your electron beams get scattered or diverged. So you have to do the processing in vacuum. And then the bed that you are melting using the electron beam also is at higher temperature. Basically, for a better coupling of the beam and the electron beam is first scanned on the bed to form a cake first, and then the melting scan happens, because of which there is the bed is maintained at 650 degrees centigrade, and then once you have a higher bed temperature, the thermal gradients that the melting and solidification layer will experience will be less, and because of which you have less residual stresses. So that's why I wrote here no residual internal stresses, because of the constant build temperature, irrespective of which layer you are building it. And since there is already a cake formed in the bottom, you don't have to specifically create a support structure. When you have overhangs that you want to build, you have to build a support structure, and then on which you have to build a feature. But here you already have a cake which acts as a support structure, so you don't need to specifically build a support structure. And because of the speed and it can be mass production. I will not go into too many details, but there are some drawbacks. Only conductive materials can be handled here, and then sometimes because you have to create a vacuum, very fine powders can create situations for you to create the vacuum that you're looking for. So there is a variant coming up. Instead of using powder, you use wires. Use the electron beam to melt the wires, and deposition. You can see a machine from Siyaki. Substantial increase in the deposition rates are possible now using such machines. And then the size of the components also, like 6 meters by 1.2, 1.2 meters, using 2 feedstocks, 2 wires, 2-wire feed systems, and deposit large amount of material. So this is a trend now. Large component can be manufactured at high deposition rates. Now, if you compare these 3 technologies as engineers, as a technologist, what do we always look for? We look for good accuracy, good finish, large number of materials we want to handle with a given technology. We should be able to build, we should have a range of sizes we can handle it, the kind of complexity that we want to handle it. So if you take those as your criteria for acceptance or rating a technology, this is how these 4 technologies, additive manufacturing technologies, can be mapped. When you are looking for, let us say, high surface finish and high accuracy, the green contour, you can see it, the green contour, that is the SLM method. Because we use very fine powders, we build only 30 to 40 micron or 50 micron layer using a 80 micron spot. But then today, the machines that are available, SLM machines, are not very big. So you have a debit in terms of maximum size. Same thing if you look at, you're looking for higher productivity and the size. As I mentioned earlier, it is that yellow contour that you have to look at. So EBIM, where scores over the SLM technique, right? So this is how, depending on what your application is, what you're looking for, techniques are available and you can choose from one of them. But of course, money is also important. There is also another method where you don't use heat source, but ultrasonic. Heat source also you can use, and even ultrasonic sources also you can use, where here the feedstock is neither powder nor wire. It is a foil. A foil after foil you can place instead of building the layer, and that layer is fused one to other, and then you build the component. So it is a kind of a solid state method. You are applying force to jam up layer to the layer. And the next technique is, we don't use a heat source. We don't melt and solidify material. Here we use certain binders to form the shapes. The technique of having a bed and lowering the bed layer after layer is constant. But in that given layer, formation of the shape that you're looking for is by jetting certain binder, which solidifies, dries up there and gives you a green shape and then gives you the component. So this is, we have to keep it in mind. Now, if we consolidate these three methods that I have mentioned for additive manufacturing and compare it with the technologies that we are already familiar with in manufacturing. Let us say the laser additive manufacturing or electron beam AM or using welding arc additive manufacturing to make layer by layer melting and solidification. It is similar to multi-pass welding. The ultrasonic method that I have mentioned is similar to solid state welding. It is high strain rate thermomechanical deformation. And if you are looking at the binder jetting method, there also it is, for example, we are making a shape and making a green component using a binder and then debinding it and then sintering it and getting a component. Same we do in powder metallurgy. So a lot of our knowledge from these fields can be brought into additive manufacturing to successfully understand it and then implement it for our applications. So those of you who are familiar with welding, for example, the moment we talk of multi-pass welding, we talk of what kind of interface we are forming, like fusion defects can be there, cracks can be there, porosity can be there, inclusions can be there. All these issues we are aware of, and similar things are possible in case of the layer by layer building of components in melting and solidification. In fact, when you talk of multi-pass welding, maximum in a 10 mm thick plate, you will complete in about 3 to 4 passes or 5 passes. But in case of this layer by layer deposition, you have multiple passes for one layer itself, and layer by layer, it runs into hundreds of thousands of passes. So you can imagine the kind of potential for defect creation. So we have to be very, very carefully designing the process. That's what I have tried to talk here. The process design and parameters choice is very, very important to get quality products. Here on the left side, you can see the comparison of laser powder bed technique, powder fusion technique, the binder jet technique. There are several input parameters, the understanding of the process physics, and the output, depending on your geometry, what microstructure you are leading to, what cracks that may come, defects like porosity, stresses, roughness, dilution. All these things are the output that you end up with, which is dependent on the physics that goes into the process, and then the input parameters, right? So when I consider as the input parameters, it can be material properties, it can be the powder properties, the simple feedstock properties. When you compare laser powder bed versus laser powder feed, the powder feed rate is the additional parameter in addition to the laser properties. Then the type of the motion device or the motion table that you have will also decide the accuracy that you will get. So this is to give you an idea of overall landscape of the process challenges that one comes across in understanding the process of additive manufacturing. I'll give you a couple of examples also how it affects. The first one is take the case of material itself. Why is it so critical? In both, whether it is powder bed where we are spreading the layer of powders or we are blowing the powders in the case of direct energy deposition, the flowability of the powder is very important. So first parameter, then that comes from the morphology of the powders. So we need spherical powders. And when we have melted and solidified, what we are looking for is 100% density in the part. So for that, you need the right kind of combination of bimodal distribution of these spherical particles. What you see a graph here is the packing density should be highest. What you see here is combination of particle sizes, which will decide the range of size, the size distribution of particles that you should choose for a SLM method or a electron beam method. Because in electron beam, we have already seen if it is too fine, the vacuum can cross problems, and then the problems of electrostatic charge can also come up. And then the powders are produced and supplied by different suppliers from all around the world. We found that there may be a variation in the process behavior with supplier to supplier also. We have seen that. So this is another one challenge. And within the powders, what should be the quality of the powder? These are all the defects that we encounter when you look at the powders, like open porosity, the satellites of small powder particles on the bigger particle. This kind of problems, for example, the open porosity particles, when you use, you end up with porosity in your part. When you use the satellited particles, you end up with higher surface finish, surface roughness, difficult to manage your surface finish. And then even after having good quality powders, as I said earlier, when you do multiple melting and certifications, you can end up with porosities in the interface of various processes. And what you see here is the speed at the amount of laser energy you are putting into melting, and then the speed at which you are scanning the surface. If you plot these into y and x axis like this, what you see here is if you put as much energy as possible, you will nicely fuse it. And then, but you have to go very slow, and that results in low efficiency. But if you want to increase efficiency and scan very fast, the quality of the material in terms of getting the density that you're looking for and the porosity, minimal porosity that you are looking for will be changing. So there is a clear optimization need here in terms of speed versus energy to have a feasible, acceptable efficiency as well as quality of the build. For example, then the next parameter, when you scan, you have the laser beam scanning one line, and after that, next line is overlapping the first line. So that depends on the size of the spot of your laser beam. In such case, you can see here the effect of hatch spacing. The line to line distance is called the hatch spacing, and you have the spot size. Even the ratio of the hatch spacing to spot size can decide the kind of density that you can arrive at. So you can see the window, the variation that can happen depending on the hatch spacing and spot size. This is another optimization process related R&D that you can do. Even in the case of simple binder jetting method, the choice of your binder, if the drying time is too less, then the penetration into the bottom layers will get restricted and you end up with poor quality of your green compact. So you have key stages of quality check in additive manufacturing, right from the raw material quality to the process, as well as the final part itself has to be checked so that it is acceptable to the user. So ASM expanded additive manufacturing capability by adding 2 new labs itself for making the technology more robust. Like they called it they added a powder characterization lab and a computed tomography lab to check the quality of their built parts right from the feedstock. And then even the NIST of US has created a measurement science program for additive manufacturing. What they are doing there is characterization of the AM materials, real-time control of AM processes like in situ sensing and monitoring and feedback control, then qualification of AM materials, processes and parts. Like we know we have standards and guidelines for codes for welded parts, forged parts, cast parts. Similar codes are to be made available for AM parts. And then even system integration to make the process robust. For example, there are 2 systems in the market already by 2 companies, Renishaw. So we talked about the importance of laser energy that has to be put for getting the right kind of melt pool size so that the defects are less. And what they do is they call it a laser view module using a photosensor to measure the intensity of the laser energy. That is matched with the library of information that is available for a given material. When this intensity has scanned a particular location, we are sure that we are having the right amount of melting and solidification. And then melt view captures the emissions coming from the melt pool. And from the melt pool, what kind of dynamics is happening in the melt pool solidification is picked up. And during the process itself, one can tell you have a defect there or not. And then they are compared. And then because it's a long process, you cannot do all this process at the end of the whole component build. And then 40 hours, 50 hours of build time is wasted. So in situ monitoring and feedback is very important. So if you combine all this in terms of what are the key technical challenges one has to keep in mind. Defect-free builds we want. We want to maintain dimensional accuracy. Material is very expensive, so we should be able to reuse the material. Then the properties in all directions should be similar. Otherwise, designers have some doubts in their mind whether what properties they should use while designing, because the microstructure that you end up with when you melt and solidify varies with the kind of thermal history that a particular location undergoes. For example, in this case, when you do build layer by layer, the XY plane properties and the Z properties can be different. So that isotropy is disturbed in this process inherently by the nature of the process itself. So we have to have methods for getting isotropic properties. And then when you do building of the components, you have complicated geometries. The stress patterns are different depending on the geometry, and they can lead to deformations. And then we talked about build size limitations. And also I talked about qualification and certification of structural parts. So those of you, you are all academics. When you take up a research problem, these are the areas in which you can look for launching a research problem and research work. We also have encountered, we have last 3 years, we have been working on an SLM method. And there are certain practical problems. For example, if the machine is being used for making stainless steel parts, and we want to change it from that to a nickel-based powder additive manufacturing, it is taking 2 days for changing from one powder to other in the present technology. The build chamber, because you can't allow contamination of the new material with the old material. So it is very tricky to see that it is thoroughly cleaned and then you switch from one over to the, and then powder loader jamming. These are some practical problems, so which we are working along with the machine supplier so that the next versions of the machine can solve these problems. The other problem is, we talked about the size limitation. Why it is today a powder bed AM system at 2 into 1000 watts laser is available, or a 4 into 400 watts laser is available, and still they are able to cover a bed size of about 500 mm, half a meter by 280 by 325. Still those limitations are being worked on. For example, you take the case of SLM alone, who is our partner in setting up our center here at ARCI. You can see the trajectory in the direction in which the machine development is going in terms of productivity, going from a 400 watts laser to what we have today to 2 into 400 watts, which results in higher 235% increase in the productivity, and then like that, 4 into 400 watts, like that. So this is the trajectory with which machine developments are happening. So I also mentioned about the constraints from economic point of view in the case of absorption of additive technology. Today, predominantly the powders that we are asked to use are proprietary to the machine suppliers because of the various challenges that I have mentioned. Supplier to supplier, also the behavior of the machine as well as the metallurgy that you end up with changes, because of which the machine suppliers also are quoting very big prices, $100 to $400 per kilogram. and then depending on whether it is aluminum alloy or titanium alloy. And then the machine costs are also very, very high capital intensive, $0.5 million to $2 million. So it says that the production rate and the productivity is also not very high, about 2 tons per year. So machine hourly rate is about $50 US. So all these costs, when you amortize over a number of units produced, hover around about hundreds of dollars per kilogram, and whereas tens of dollars is what current conventional manufacturing processes can deliver. So if you compare the behavior in terms of where you should consider AM as a potential technique, production volume versus the complexity of the top graph on the right side is the cost of a unit using additive manufacturing is that horizontal line. And in the case of a traditional manufacturing, it is like it's a sloping down line like a hyperbola. So when you have low volume in the traditional manufacturing, it is high cost. But when the high volume production is there, it goes very, very cheap in conventional traditional manufacturing. But additive manufacturing, it remains like that. But when you want to use the technology for complex shapes, the curve changes. If you consider additive manufacturing, costs remain same, whether it is complex part or a simple part. The additive manufacturing costs are much lower when it goes to as the complexity of customization important. The message is, if you want to have less number of parts with high value addition, high complexity, as on today, AM is a good choice. Probably in future, we may be able to modify this curve a little bit, but that is some way away. Now we talked about the technology, the process challenges, the economic challenges. Now let us look at the more in-depth analysis of the metallurgical challenges involved in the metal additive manufacturing. I talked about the anisotropy, that is the behavior in the XY plane and then the Z direction. So why this happens? As the heat dissipation while melting and solidification happens through the build direction, it is higher, the heat dissipation, compared to the other direction. So solidification in that direction results in anisotropy in grain morphology and consequently the mechanical properties. In laser processing, the melt pool size is so small that the material goes through rapid cooling, almost 10,000 Kelvin per second, leading to very fine microstructures and very small heat affected zones. And another thing that happens is repeated melting, because we are doing layer by layer. So you put a layer and then you're putting the second layer. When you do the second layer, some amount of remelting takes. Hello? Hello?
Sir, we are able to see, sir. We are able to see.
You are able to see, no? Okay.
Please.
Because here power went off here.
Yeah, no, it's okay, sir. You can continue.
Okay. Yeah. And then the layers that you have built in the past, as you are building the Z planes, those bottom layers are experiencing repeated heating cycles and cooling cycles. So, and another thing is different zones experience different gradients and solidification rates. And then the solidification morphology changes from sometimes even from a cellular to a dendritic to equiaxed grains. So all that will reflect in the mechanical properties. and the other heterogeneities that we create. We talk of welding also. All the research is about making as homogeneous materials as possible so that the properties are predictable. That is like the lack of fusion, surface finish, and varying thermal gradients resulting in residual stress. So these are the challenges that we encounter while doing metal additive manufacturing. Now, all that metallurgy that I mentioned, like rapid solidification, the defect formation, the fusion behavior, all that changes again with material to material. So there are some commonly used alloys, I call them the AM-friendly materials. Then the materials which are still, as on today, challenging for additive manufacturing. A lot of research is going on to bring these challenging materials also into the ambit of additive manufacturing. So why some of them are friendly, why challenges are there, and some of them are still to be researched. I'll just give you some examples. Let us take the ferrous materials. As it stands today, there are these are all the list of steels that are used: Maraging steels, Mart 420 grade, 17.4 pH steels, 304, 316 stainless steels, tool steels, H30 tool steel, low alloy steels. Pure iron also is used for additive manufacturing today. But predominantly, if you see which technique is being used, it is the laser powder bed technique, little bit only electron beam, because in steel, the oxidation is not an issue. So electron beam is an overkill for additive manufacturing of ferrous materials. And then you have laser powder fusion methods also used substantially. And within that, if you see the bar chart, number of research papers, Maraging steel is the highest number of publications. And then the stainless steel, these are all well-studied materials. So a lot of applications are also there in these materials only. And the reason is, take the case of 316L. It's an austenitic stainless steel, a single phase material. Single austenite phase is there. And then density is achievable as theoretical almost, 7.94 versus 8 grams per cc. And when you look at the microstructure of this AM built layers, you can see in the left top microstructure, each of those melt pool boundaries and all that, the layers, you can see a typical microstructure. Can you just give me a second? Just give me a second. Huh?
Please, sir, please.
So we can see effects of rapid solidification in terms of a cellular microstructure, very low angle grain boundaries. You can also see high dislocation densities at grain boundaries with some ferrite retention, which gives you ductility also. So these are the features, typical features we encounter in an AM built stainless steel, even if it's a single phase material. And what it shows up as, you can see the yield strength from a conventional property of 170 megapascals to a 441 or a 399 in the two directions of the samples taken from an AM built structure. And typically, this is coming from the microstructure, which I have explained. And but stainless steels are mainly meant for high corrosion resistance, especially pitting corrosion resistance. That also you can see from the potentiodynamic polarization curves, that the AM built SS316L is superior to the ROT 316L. You can see the corrosion rate, right? Even the corrosion voltage shows that it is superior. And why is it happening is, if you just take element mapping across a usual conclusion that is there, you can see the manganese sulfide formation is suppressed, because of which chromium depletion is also suppressed, resulting in better pitting corrosion resistance in this material. And take the other material, like the dye materials, Maraging steels or the hot work tool steels like H13. Here you want high temperature properties. And normally to achieve these properties, you have certain very elaborate heat treatment cycles that you look for very fine distribution of the hard carbides, which do not coarsen but give you high temperature properties in conventional method. That when we did additive manufacturing of H13 tool steels, what I'm presenting is actual work done in our lab. So different power and scan speed combinations. You can see the density achieved as well as the first surface finish achieved. Selected parameters in terms of scanning speed and power have been used. And these are the microstructure of the selected one. And a simple heat treatment of about 620 degrees centigrade of post heat treatment. You can see the structure changing. You see the diagram D. You can hear. Professor Ramakrishna, you can hear, no?
Yeah, I'm here, sir. I'm able to hear, sir.
You are able to hear, right?
I'm able to hear, sir.
We are able to achieve, just build a tool or the part and just give a 620 degrees centigrade treatment, and then you have broken the cast structure and also retained the carbides that are required in the grains as well as at the grain boundaries, giving you the high temperature properties. A very detailed metallurgical analysis of phase analysis and using the X-ray residual stress measurement methods, the crystallite sizes have been calculated and the microstrains have been calculated. And using these values, you can see here using the equation on the bottom, we calculated theoretically how much dislocation density is there in different heat treated conditions. And you can clearly see that AMH13 has got the highest of dislocation density, which impedes the motion of dislocations and then giving the higher properties that you're looking for. So AM is a beneficial process for this kind of a steel. That is clearly reflected in the case of the properties you're getting from the AM built H13 tool steels. So that is coming from refined sub-nano size carbide precipitates within and around bundles of martensite. And then chrome moly and tungsten get enriched in the alpha phase to form BCT martensite. And because all this is due to high cooling rates encountered in the SLM process, and advantages are simple heat treatment. And once you are able to use AM, you can build conformal cooling channels. And then, of course, good hot hardness implies better tool life. So this is a good AM-friendly material. Let us look at non-ferrous materials. When we handle aluminum, we have defects caused by thin oxide films. And then these oxide films have to be, focus should be on avoiding formation of oxide films through Marangoni effects. And then high volumetric contraction and thermal expansion leads to other issues like stresses, etc. These are all issues. And then one of the popular material which is friendly with AM is aluminum silicon magnesium alloy. And you can see in the microstructure, you can see aluminum silicon eutectic is nicely uniformly distributed in additive manufactured part rather than the cast part. The left one is the cast and the right one is the AM one. You can see the fine distribution. And then we have done a lot of experimentation of AM of this alloy, and you can see the properties. I'll just concentrate on that part. The last row, ASM, is the standard properties that we have got here in terms of both yield strength, ultimate strength, as well as elongation. All the properties have improved in the case of additive manufacturing. And all this is because of formation of dislocations. You can see in the microstructure because of the rapid dislocation, rapid solidification process. And also in the as-built condition itself, we have the precipitates, Mg2Si precipitates, which strengthen the material. So again, the process gives you an advantage. That's what I have said already. And also there is innovative possibility of avoiding the solidification problem by nano-functionalization by adding elements like zirconium so that heterogeneous nucleation is promoted. And you can avoid the segregation pattern as top picture and end up with very fine grained structure, which helps in getting the good properties that you're looking for. Similarly, go on to the titanium alloys. I think we are now a little bit running short of How much time do you have?
Sir, still you have time, sir. It is only you can have another 15-20 minutes. 20 minutes, no problem.
No problem.
No problem, sir. You can proceed, sir. No,
I hope it is not an overdose.
no, it's not, sir. It's very interesting, sir. Actually, in-depth studies. Because most of the faculty, most of the people are faculty, they can select the research problems from these studies. It's very useful.
Okay. So then
You can continue.
I will load you with more and more. No problem.
No problem, sir. Because very less people will get this information outside, sir. Text anywhere, literature, we cannot get all this.
Yeah.
Yes, proceed.
So the next great material is the titanium alloys. You know why they are important. Aerospace sector uses it extensively. A high specific strength material with good fracture toughness, high fatigue behavior, less corrosion, even biocompatibility for biomedical applications. But it's not an easy to machine material and has very low thermal conductivity and high reactivity. And that's the reason it becomes a nice candidate for additive manufacturing. And because casting process also is tricky, welding is also a little tricky, and generally machined, that's the reason. And from forged blanks, and especially in aerospace industries, there are components where 95% material is machined off to get the final shape that you're looking for. So considering the technological advantages and the metallurgical advantages, titanium became a darling material for additive manufacturing. But it's not challenge free. Just look at this microstructure when you build layer by layer. I already talked about the porosity formation, but here we also found difference between if the powder is made porosity is different. The percentage porosity is varying depending on what process you have used. Yeah. The next problem we are facing is on the left, you will find that AM built Ti6-4, titanium 6 aluminum 4 vanadium material in the SLM method, UV melting method, and the direct energy deposition using powder or wire method. So what you have the left column micrographs and the right column micrographs is the bottom layers and the top layers, right? What you have, you can see the variations in terms of in each of the process itself from top to bottom. There is variation from a fully martensitic structure to a martensite plus partially decomposed martensite, or a combination of lamellar alpha beta. So the top regions remain above beta trances. Bottom regions undergo repeated heating and cooling cycles below the beta trances, resulting in inhomogeneous microstructure. So you can see in this one picture the inhomogeneity that your microstructure you are creating, both from process dependent inhomogeneity as well as the layer to layer inhomogeneity in the Z direction. So one has to be conscious of, we can end up with this kind of inhomogeneity, and we should know how to deal with it through post-processing heat treatments. This one, if you put it schematically, microstructural evolution map, starting from base metal microstructure to the top microstructure, you can see at the top you have, these are all the pictures at different layers. A total beta structure on the top to an alpha beta structure and a beta structure in alternating, and the bottommost having an alpha prime plus martensite structure. So this is another. And then directionality issues, isotropy I talked about. If you take specimens in 3 different directions as shown here, and you can also see the stress strain curves of these 3 specimens. They are so different. The one which is taken in the XY plane is showing a nice ductility. You can see the strain, much larger strain compared to the specimens taken in other directions, right? And this is because of the nature in which that you have built the component. In vertical direction, you have layer by layer, and if any small defect in those layers can result in the you can call it the delamination and failure. Then similarly, but people have been able to overcome this problem by doing post-heat treatment and then get back the elongation that you are looking for by doing something called hot isostatic pressing. Hot isostatic pressing, what it does is simultaneous application of high temperature and pressure. Like we have a hip in RCA, 2000 degrees centigrade, 2000 bar pressure we can apply simultaneously, because of which the porosity gets closed and certain grain coarsening will happen and then homogenization will happen and you will end up with better properties. So when you talk of titanium 6 aluminum 4V material, we always look for a bimodal structure like globular alpha plus fine lamellar obtained by the solution treatment and aged condition. It gives the right combination of properties like specific strength and the toughness and fatigue behavior we are looking for, which is unachievable by AM, but good properties could be achieved if we can do in situ martensite decomposition to lamellar alpha beta. So this is too much getting into the molecular level or phase level transformations that we are looking for. This is a subject for 1 hour talk. I would not like to go too much into it. So by intermediate mechanical deformation also people are able to achieve the properties that they are looking for. The next alloy is the most popular alloy is the nickel-based superalloy used in blades of gas turbines, rocket engines, turbine blades. This is also a complex material. We have strengthening phases like the gamma prime or the gamma double prime in a gamma matrix and the undesirable phase like a lavish phase. So the whole solidification behavior and the heat treatment behavior has to be optimized to minimize the lavish and maximize your gamma double prime or gamma prime phase in the material. And we did extensive work. We make this powder in our own lab, and then you can see here the kind of powder size distribution we are able to achieve in our lab, and then compare it with commercially available iron 718 powders, and studied the NB niobium segregation in this alloy, so that because that determines the amount of the precipitation behavior in this alloy. So a PhD thesis is being done by one of our scientists on this particular aspect alone, and we use these materials to build AM parts, and you can see the top two stress strain curves of this alloy made from commercially available 718 powder and powders made at RCA. You can see a perfect match in terms of the stress strain curves. So what I mean to say is we are able to make indigenous powders, and in this case the powders, the material is reasonably AM friendly, and we also saw that the wrought material as well as the AM built material are behaving or responding to the heat treatment in a similar fashion, and the volume fraction and distribution of several phases is also same in both the cases, because of which we'll be able to predict the product properties better and implement this material, AM material, into production. Now I go to a little challenging material like copper. Several of copper components, when you irradiate a laser beam, it reflects off. So melting copper is a real challenge. It's not easy, and that too to get your fine features because of the high heat dissipation that happens. But today, now even copper is made amenable, and a lot of tooling where thermal management is required using copper materials are being made with the conformal cooling channels using copper material. In fact, Fraunhofer has published this. ILT in Aachen have done it, and then they have done it using a green laser, a very special laser that has been built for this and used for additive manufacturing. In fact, they have showcased even induction coils made out of copper using a special green laser. And we all talk about electric vehicles and electric mobility these days. And electric mobility means you need to have your motors, the stators and the windings that go into it, and the copper bars instead of winding wires for radial flow and then axial flow and cross flow. The hairpins, they are able to 3D print now, and you can see the parts that they have been created and then assembled it into a motor. And then today, it's going to be a reality, more or less. It's in the prototype stage, but even 3D printed motors are going to come. Similarly, electric mobility requires magnetic materials with high BH product. Conventionally, melting, crushing, milling, magnetization for high alignment of your domains, sintering, annealing, and then oxidation by plating on the top. This is the several steps through which you manufacture magnets. But when you use additive manufacturing for magnetic materials, today even the FDM method as well as the selective laser melting methods have been used to make permanent magnets. Almost 45% magnetic materials, magnetic particles have been put into plastic, thermoplastic filament, and FDM method is used to make the shapes of the magnets that we are looking for. And then magnets are being made. In the SLF method of the permanent, the most popular NdFeB magnet with a BH max of about 45 kilojoules per meter cubed is without a post-heat treatment is achievable today. Similarly, the Alnico type. So these are, we know that these are the two popular magnetic materials. Some good amount of recent work has given good promise in terms of application of AM to magnetic materials. In fact, what you see here is a actual prototype developed by the Oak Ridge National Lab, a prototype of the Fi3 silicon stators and then NdFeB magnet motors, the permanent soft hard magnet combination. Now coming to a few examples of AM at ERCA, the metal powder additive manufacturing. I have already talked quite a bit about what we have already done. That is about the metallurgical part, what I have mentioned earlier. Now I'll just show you some typical examples which are developed and put into use also. Starting from metal powder manufacturing to design, to actual additive manufacturing, to post-heat treatment, to characterization and texting. The whole value chain is addressed under different groups of our lab. You can see the facilities shown here. As far as the additive manufacturing facilities are concerned, we have powder bed additive manufacturing using lasers, 2 SLM machines, and then we have laser direct energy deposition machine using a robotic deposition system, and we have the RCAM EB powder bed fusion technique, and then we have a laser wire deposition system, and then we have cold metal transfer for wire additive manufacturing, and then extrusion based ceramic 3D printing, and then even cold spray coating technology which can be used for 3D printing, mainly for repair applications. So these are all various techniques of AM that we have. And then we have addressed several applications. It's partial lists, about 15 applications are listed here. Starting from the valve black, I've shown a video of, to a pressure die casting tool, to a nozzle guide vane, to mesoporous structures. But whatever application you take, it starts from the choice of material and its behavior to design for additive manufacturing. The 3D model or the slicing, the topology optimization, the orientation, the building process optimization, stress relieving, post-processing of stress relieving, support removal, improving the surface finish through short blasting, etc., or any other method, heat treatment, and then dimensional accuracy, and then testing and validation. So this whole value chain we have to go through before we put a technology or a component into service. And we go through the whole value chain. And some of those red boxes on the end are the actual ones finally even industrially accepted also. So in this matrix of material, application versus the various process steps that are involved in additive manufacturing technology, the intersection of these points, the horizontals and verticals, each of these areas are potential research areas. So one of the examples is a pressure die casting die for conformal cooling. You can see the spiraling cooling channel and a semicircular or hemispherical top end that you can see in the picture. And this gives you effective cooling. We have made using additive manufacturing, and this has been put in actual pressure die casting industry. And you can see without cooling channel and with cooling channel, the core pin temperature is less by about 20 degrees, resulting in less of heat checks and porosity. And that's almost 30,000 shots already done, and industry is happy with this. And the direction control wall, the video which you have seen, starting from a solid block on the left side to the actual design which is showing in the red color or the middle one. What we did is first started with a skeleton of the flow patterns that are required and started adding material virtually through the CAE, and then depending on the stresses that are expected and adding a factor of safety, added the material knowing the properties and arrived at this design. So finally, with a factor of safety of 5.7, thinking that we should be able to withstand a 5.5 megapascals von Mises stress, we are able to achieve a design with 58% weight reduction. Then we had another electronic component. You can see the dimensions here. There are features of about 0.51 millimeters also. And then this is a typical microwave device, a Ka blind slow wave structure. I am giving typical examples here. And this is made out of copper. Now, using our SLM machine, this is not possible because it reflects off all the material, all the laser radiation. So what we did was, first did experimentation in terms of building the features with the more friendly 316L on a copper plate. Did all the mechanical interface or metallurgical interface studies and the mechanical property studies, found that it is mechanically good, and then took a copper block and built the steel features onto it, and then electropolished it and got the component that we are looking for. So this is what I call hybridization of the additive manufacturing methods. Next one was a honeycomb kind of a structure with, you can see that porous structure, the vertical channels, and this should have a particular shock attenuation property. This also is used in certain missile applications. So when something comes and hits, it should get collapsed and absorb the impact energy. So depending on the shape of these channels, the wall thickness, the shock attenuation capabilities will change. So depending on the user requirement, these channels were designed and built, and you can see the actual experimental design that the desired shock attenuation has been achieved. This is a vane used in the high pressure turbine of an aircraft engine. So it is a nickel-based superalloy product. The vane is so complicated in geometry, it is presently being made using investment casting followed by drilling using lasers for cooling holes. And what you see here on the right side is the conventionally made component, and on the left side is the AM built component. In one go, all the features that are required, including holes, could be built in additive manufacturing. This I can say presently we have achieved the geometry required, but a lot of other tests are to be done before it is finally accepted. Like this, there are numerous examples on which, like on the left side, a hair transplantation device, then micro heat exchangers, a spacer for the nuclear fuel bundles, a convergent divergent hoses, a double-walled nozzle for certain flow applications. There are numerous applications that we have done in the lab. And we also have a lot of interaction with industry, and a lot of them come for training to us, and we provide a training program. This was one of those pictures that we have done for both our own SLM partner. Their own customer came and got trained in our lab, and even Cyient, which is former Infotech, sent 2 teams for training. So we are also sharing knowledge. And to summarize, each material has unique behavior under AM processing conditions and requires process optimization to obtain defect-free builds. we have to tackle the anisotropy of properties. Generally offers fine microstructures which are beneficial in terms of mechanical behavior. There is variability of properties among the materials processed by different techniques. And then AM processed materials behave differently compared to conventional processed materials, as it is a highly non-equilibrium process. And great deal of research needs to be carried out to increase the understanding so that a wider range of materials are available and further increase the potential of this technology. And then the recent trends in terms of the technology is recent increased productivity using multiple lasers, hybrid manufacturing that I mentioned. And then I also talked about quality, in situ monitoring and quality assurance. Then open materials model, software to predict, correct, and manage print parts, and automated solutions for post-processing, part cleaning. These are all the technology-oriented trends in which work can be done from the process technology point of view. So in the interest of time, I think I will close it with metals. I will only make a couple of remarks about the other materials. For example, additive manufacturing of ceramics. You can see the kind of trend, number of patents that are getting filed, the way it is increasing, additive manufacturing. And predominantly it is in the maximum in the healthcare sector, and about 54% orthopedics and dental implants. And then various techniques are available now, lithography-based ceramic manufacturing. Basically, you have a ceramic suspension in a binder, photopolymerizable binder, and with a UV laser, you do the shaping. Similarly, we have SLM itself with a preheating so that melting actually can be done. Then we have the selective laser curing method, where we start with a binder and a silicon carbide particle put together, pyrolyzed after 3D printing. And then the porosity that you end up with is infiltrated with silicon, and then you get a good part. Similarly, silicon carbide is a very highly technologically important material. Very fine features can be built using the binder jetting method of ceramics. And at ARCI, we use the extrusion method to make different ceramic shapes, which you are seeing here. And one of our innovations has been using 3D forming of spinel ceramics by gelation, thermal gelation techniques. And you can see that you make the paste using methyl cellulase, and then 3D print, and then thermal gelation, and get the green samples, and then sintering. Then you get the density what you're looking for, and you can see a comparable property to slip casting samples. And also, we can do pressureless sintering, even ceramic replication of 3D printed PLA polymers is another. And then functional materials are also additively manufacturable. I'll give an example. What is a solid oxide fuel cell? Is an anode supported or a electrolyte supported electrolytic cell. Basically, it's a ceramic material. On one side, you have nickel stabilized zirconia, you have yttrium stabilized zirconia, and another side you have the lanthanum strontium manganate. And this is 3D printable using these three different materials. And you have enough literature available, and comparable open circuit voltage is achievable using 3D printing of solid oxide fuel cells. And for that matter, there are also experimentation in terms of using material on the moon to 3D print using lunar soil simulated material by geopolymerization method, and 3D print such structures that whenever we go to moon, we can do 3D printing of livable spaces using 3D printing. This is only a dream. I just wanted to close with it. And any advanced technology passes through something called a Gartner's hype curve. Starting from some innovation trigger immediately everybody thinks it has great potential, and then there will be peak of inflated expectations. You can see the peak. It goes to the peak, and as the challenges we are realizing, slowly there will be a trough of disillusionment. And some of the players which are able to understand the technology better, they continue to work on it and slowly solve one problem after the other and up the slope of enlightenment and then reach a plateau of productivity. This is a classic trend that we see in case of any modern technology development. And this is a Gartner's hype curve for 3D printing. I'll just only show a couple of points here. You look at something like, let us say those dark blue things or light blue things. You see here that 3D printed tooling, jigs and fixtures, 2 to 5 years time, it will be in the plateau. That's the expectation. And we are already seeing it. And I've shown you several examples how metal 3D printing is penetrating into tooling industry. Okay, so I would like to end here. This is all my team of people who are working on additive manufacturing, very hardworking scientists and students. You can see the kind of hard work they put by sitting and cleaning each part of the machine before changing from one material to the other. That's the scene here. So I thank all my colleagues, Ravi Bate, Guru Raj, Manish, Ramakrishna, Divya, Venkatrao, Santosh, and many other students who have been working on this AM technology. And it is their work that I have presented. I would like to acknowledge all of them and thank you all for your attention. Thank you very much.
Sir, thank you, sir, for a very wonderful, exhaustive, elaborative session, sir. Truly, it is a keynote session for our FDP program, a launchpad, because it's very essential, sir. When you start a program for 5 weeks, we should have such kind of motivation given to all the faculty members. I hope most of them got now so many research problems. They can pursue their PhD work, and it's a very practically oriented. I think in literature also you will not get all these things information, sir. In fact, we visited your ARC also, sir, before we procured our SLM machine to our center. So we have seen how elaborate the work goes on and tremendous amount of research ARC does. So thank you, sir, for your valuable address to our audience. There are few questions from the audience, sir. Can we answer, sir? Few questions.
Yeah. I can take.
So I am going to read it, sir. It is in the chat box they posted. Now, one question is from Vijay Gajapati Verma. He says, why are there no residual stresses in electron arc beam melting?
In electron beam melting, I already mentioned that there is a preheating that is done before melting. Once you preheat to about 650 degrees centigrade, the overall thermal gradient that exists during the cooling phase is much smaller. Once you have a low thermal gradient, you will have less residual stresses.
Another question is from Srinivasan. He says, kindly share some insight on AMO flexible electronics and facility details available in India, flexible electronics.
I am not familiar much with this area. In the last, I have briefly mentioned about the AMO functional materials. And one of the techniques there, a couple of techniques that I mentioned is photolithography and the inkjet printing methods. Okay. To my knowledge, these are the two techniques that are possibly used in flexible electronics also. But I will not be able to comment more than that because I have no real exposure. Yeah.
One more question is from a lot of people are asking, sir. We'll close with 1 or 2 questions. It's a very interesting, there's a lot of interaction. Rupa Tulasi asks, how cost optimization can be made when SLS process is used, especially in implant applications?
See, cost optimization can come from several stages of this technology. It can come from having cheaper material. It can come from higher deposition rates and lower rejection rates. And it can come from reduction in any post-processing steps that may be required in terms of surface finish or the heat treatment that is required. So there are various steps in which you will have to work on where you can reduce the whole value chain complexity so that cost can come down. And also in terms of even in the step of how you mesh them in the bed, how many of them you can build in one bed in 280 by 280, how you can optimize number of components we made in single bed. So there is no single solution, and we have to work on cost reduction in each of the steps. And we are open to, if she is from an industry who is looking for that kind of help, we are ready to work with them and help them out.
Thank you, sir. What is, this is Shivakrishna asking, sir, what is 4D printing? How it is different from 3D printing process?
No idea. I have no idea.
It's still in the imagination, I think. Mm.
Yeah, people talk several things. They print here, they print something else. Anyway, I would not. I would restrain from commenting on that. Yeah.
So, sir, one participant want to speak, sir. Say his view on this, sir. Hanuman Dora, I think.
Please.
Hanuman Dora, you can please proceed. Switch on your video, yes, Hanuman Dora. Yeah.
Yes, sir. Yes.
Yeah, please, you can switch on your video. Please speak up.
Hello.
Yeah, please speak.
Is it coming, sir?
Yeah, please switch on your video. Otherwise, you can speak, please. Yeah.
It's coming. Okay.
Please speak, please.
Hello.
Please continue. Yeah.
Good afternoon, sir. This is H.K. Dora, Krishnamurthy Dora speaking from Moksamja College of Engineering. Thank you so much for your wonderful inaugural session. I mean, like first presentation, sir. And really, it was so much informative and it was motivating that starting from the scratch, from the definition to the highest level of research orientation, you had taken us like a flight taking off from the ground to the highest level. And we really enjoyed and learned a lot of things about additive manufacturing. And to be very frank, I know very less about it, but within this 1.5 hour, 2 hours, I have almost got my background in metallurgy and all these things. I could understand everything what you have said, and the casting process and production process, whatever that we have the background. So we are very fortunate to have you today in the morning session, sir, as a first keynote speaker, and we are really enlightened to be in your presence in the morning. And I hope it will open up for so many people. Even I am doing a research in Osmania University. It will open up problems for many people to do the research on this particular area, the latest 3D printing technologies and additive manufacturing. Thank you so much, sir, for a wonderful session. Thank you.
Yeah.
Thanks.
Yeah, it was my pleasure. I hope I have been able to convey something. Thank you very much.
The last question, sir. One question from Johnson. How can we reinforce the strength of AM parts compared to similar conventional parts? Also, the cost of AM parts are higher than conventional parts.
We can reinforce.
Reinforce the strength of AM parts compared to similar conventional parts. Reinforce.
I'm not getting the point. If he can tell me how he reinforces conventional parts, I can tell what he means by that. So you can do, for example, when you talk of components, composite materials, it comes from the reinforcing filler that you put into it. But from the design point of view, you only design in such a way that you have certain fillets or certain brackets kind of structures so that you can reinforce. But specifically, this is also a melting solidification technique. It's only a shaping technique. How you want to reinforce. But there are some innovative methods I mentioned that you can have some, let us say in the case of aluminum alloy, where the typical columnar dendritic structure can be broken by putting certain heterogeneous nuclei in the nanoparticle form, and then break that structure and then have some equiaxed grains so that you get a better strength. So that is from solidification point of view. So they can write to me whatever questions they have. I'm open. I'm okay. Depending on my availability, my time constraints, in a day or two or a week, answer will come to them. If not me, my team members will send an answer to them. Okay.
Definitely. Thank you, sir. And I thank all audience for their patient listening. Thank you very much, sir, for joining this session and giving inaugural speech and sparing your valuable time. I know as a director of ARC, you are engaged with so many activities, but still the interest shown by you in towards the academics, making us to learn a lot of things. Thank you very much, sir, for joining these sessions and the first session. Thank you, sir. Thank you very much. Thank you.
Thank you. Thank you.
Yeah. So I thank all audience for presenting to the first session. And now I'm going to paste the link feedback session and as well as attendance link in the chat box. Please submit that feedback and attendance sheet. We'll join exactly at 2:30 for the next session. That is as per our schedule, we'll join exactly at 2:30 for the next session. Now I'm pasting the link for your filling of the feedback and attendance sheet. Session come attendance. Please do fill it.
Okay, sir. Okay, sir.
Fill up that and you can leave. Pasted the link in the chat box. Please start submitting your feedback. This is very important. Your attendance will be counted on this only. And apart from what I am seeing, because the entire session is recorded, what I am seeing on the screen, how many people are attending, both will compare and give the attendance. So please start filling up the attendance form. I'll also please do this as are you able to open the chat box? That is a Google form, please. No.
It is in the chat box or group, sir?
I have put in the chat box. Are you able to open?
Chat box is
So I think 16 people already responded.
a chat box.
Chat box, I'll again paste in the our WhatsApp link also. Please responded already.
వాట్సాప్
Some,
గ్రూప్ అయితే ఈజీగా.
it is not okay, but I am putting in the WhatsApp group also now.
Yes, sir, thanks.
The problem is people who don't attend also will post their attendance there. That is the issue.
గ్రూప్ లో అయితే అలాగే అంత హందా ఇచ్చేస్తారు.
I think in the it's opening now. Most of people are able. The link is working. Around 20 people are done. Again, this is same again. Raghu,
yes, sir. గ్రూప్ లో వచ్చింది సార్.
పనిచేస్తుంది రెస్పాన్స్ 35 వచ్చినాయి already. I posted again in the WhatsApp group. I posted. Please try again. Please try in the WhatsApp group. I have posted. Please try again.